In this chapter, we're going to be studying amines. We'll be talking about aliphatic amines. Those are the types of amines that we covered before. And we'll also be talking a little bit more about aromatic substitution reactions, either nucleophilic or electrophilic reactions. And we'll talk about how having a nitrogen or heteroatom in the ring affects its reactivity. But for the most part, this chapter is review. It's a lot of stuff that you've either seen uh, well, it's a lot of stuff that you've seen either previously this semester or last semester. So let's go ahead and get into this. We know that amines behave like bases, or they can behave as nucleophiles. And the only real difference is whether or not the nitrogen lone pair is donating electrons to a hydrogen or another atom like a carbon. As shown here at the top, the nitrogen is acting as a nucleophile to the hydrogen and acting as a base. And here we show the nitrogen acting as a nucleophile for methyl bromide, so for the methyl group in an SN2 reaction to show the methylated amine in the product. When we talk about amines, we classify them as primary, secondary, or tertiary. And the only real difference between amines and alcohols is when we talk about a primary, secondary, or tertiary alcohol, what we're really talking about is the number of alkyl groups that are on the carbon containing the oxygen or the hydroxyl functional group. For amines, it's actually the number of alkyl groups on the nitrogen. So it's a little bit different in terms of how we sort of identify primary, secondary, or tertiary. Now, the nomenclature should be familiar to you. All you do to do the nomenclature is to say pentane, and then you replace the E with the word amine. So this is N-ethyl. Remember, in an N-ethyl, the N is acting as the locant, the position of the alkyl group on the nitrogen. And so this would be N-ethyl 1-butanamide. This would be N-ethyl N-methyl because now I have two groups on the nitrogen, one propanamine. I think I said amide before, sorry. The N again designating position, and then the functional groups being listed in alphabetical order in the name. Now, when we're looking at common names, all we do is we name the alkyl group and add the word. So this is the alkyl substituent name, and then we add the word amine. When we are looking at secondary or tertiary amines, we name the substituents on the nitrogen as alkyl groups, and then we end with the word amine. So this would be ethyl butyl, or sorry, butyl ethyl alphabetically amine, and this one would be ethyl propylamine. When we're talking about cyclic heterocycles, there's a lot of different kinds of nomenclature that gets used. I don't care that you know the common names, but I do care that you know the systematic names and how the systematic naming works. Aza is the prefix for a nitrogen in the ring. Oxa is for an oxygen in the ring, and a thia is for a sulfur in the ring. And so this, if it had been carbon, would have been cyclopropane. To say aza means that it has a nitrogen in replacement of a carbon. If you had had um, two nitrogens in the ring, let's say, I don't even know if you can make this, but let's say it was like this, then this would have been diaza, cyclopropane. And the thing you have to think about when you have more than one heteroatom in the ring is the numbering order that you give. So this would be a 1, this would be a 2, so this would be a 1,2 diazocyclopropane. If you had a substituent on it, let's say here, then you would have counted this one as 1 and then numbered the other way. If the substituent isn't on one of the nitrogens, let's say it's like here, 2-methyl azocyclohexane, well, the nitrogen gets the number 1, being the heteroatom in the ring, and then you count to the second position, 2, to give this CH3 the lowest possible number. If the substituent is on the nitrogen, just like you did when you talked about acyclic saturated compounds like regular amines, then you use the letter N to designate where on the ring you'd use the letter N to designate that the substituent is on the nitrogen. There's a lot of different pKa's. I don't care that you know all of them. Some of them you should know. That is nitrogen in general, a saturated or an aliphatic nitrogen, NH, say 2. This is going to be greater than 35 as terms of its pKa units. NH3 is 35. And adding an alkyl group, this is an electron donating group, makes it less acidic or raises the pKa, because by donating electrons to the nitrogen, it makes it better at holding on to its protons. When you have an aromatic, a nitrogen attached to an aromatic ring, then those pKa's are relatively acidic, and that's because when you think about the nitrogen, when it's deprotonated, this is aniline, so this is the anilinium ion, these electrons are delocalized by resonance, making them less able to pick up protons, and as a result, it's more strongly acidic when it's protonated, and so you get these lower pKa. So nitrogens near aromatic rings, nitrogens that are not unprotonated, these are ones that you should know. And the other class you should know is the ammonium type ions. pKa's are all around 9 to 11, somewhere in that range. So those are good ballpark. Now, some of these other ones like morpholine and quinnuclidine, I don't care if you know those values, but you'll notice these are all alkyl, and they're near that 9 to 11 range for alkyl, protonated alkyl amines. Okay, now in terms of reactivity to substitution, what we find is alkyl halides are the most reactive. So this is reactivity to substitution or elimination. We find that alkyl halides, especially like the alkyl iodides or alkyl bromides, are the most reactive. And then the reactivity essentially goes in order of decreasing acid strength. The least reactive are the groups that are the least acidic. That is, they have pKa's that are very high. And the most reactive are the ones that are the most acidic because their pKa's are relatively low. And that makes that, for example, fluorine, a much better leaving group than the amide. Again, in the form of a review, amines can be nucleophiles in a number of different ways. One way is direct SN2 reaction for replacing, let's say, a primary alkyl halide. It forms the protonated ammonium ion, and then you deprotonate to form the product. You can also do a nucleophilic acyl substitution. That is, you take the nitrogen and the This is the shortcut way of doing it. You open and you go to a tetrahedral intermediate when you do this, and then you collapse it, and then the chlorine leaves. Again, you end up with the protonated ammonium ion at the end, and so the second equivalent of amine is used for neutralizing the proton off the product to give you your product here. So one of these is involved, one of the two equivalents of methylamine is used as a base. And that's what you're seeing here, and it forms a salt with the halogen that leaves from the acyl chloride or acyl bromide. It can also be done in an addition-elimination reaction, and this is the formation of imines or enamines. And so again, trace acid, this is the lab that we're doing this week, or that I did last week, and you'll be watching this week. With distillation, it goes all the way to the imine or enamine, because you're removing the water in the product through a azeotropic distillation. And then another way, and this is maybe not all the ways that you can use amines. Amines are usually involved in conjugate addition, and so you get the enol that forms from the conjugate addition of the amine, and then when the enol collapses and tautomerizes back into the keto form, it picks up a hydrogen from the solution, which happens to be most likely the hydrogen that came from this nitrogen here, or one of its friends that looks just like it anyways. So it acts as its own base in the solution. The other thing that amines can do, and again, by way of review, is you can form diazonium salts. And these diazonium salts can be used with, for example, in the Sandemeyer reaction with a copper salt to perform substitution reactions to replace it with a nucleophile. You could replace it with hydroxide groups. You can replace it with hydrogen from hypophosphorus acid. So there's a number of things that you can do with the diazonium salt. Okay, so let's talk a little bit about aromatic heterocycles. To start with, the three that you need to know the name of are Pyrrole, furan, and thiophene. And Pyrrole, furan, and thiophene have nitrogen, oxygen, and sulfur in the rings, respectively. If you look at the electrostatic potential maps, for furan, oxygen is more electronegative, so you see a negative charge down here. It has one pair for each one of these. For each one of these, there's one pair of electrons donated into the ring. And we talked about that in the last chapter. So only one of these electron pairs, there's a hydrogen here, so that obviously can't go, but this pair. And then one of them is in the plane of the molecule. In the case of Pyrrole, the hydrogen is in the plane of the molecule, and one lone pair from each of these molecules contributes to the ring to make it aromatic. And again, we're talking about Huckel's rule, so the molecule needs to be planar, and there needs to be an odd number of electron pairs. And one of the lone pairs on the heteroatom provides the odd number, so it can be aromatic. Now, an interesting thing about Pyrrole, because Pyrrole already has a hydrogen attached to it, when you look at its resonance structures, you get a significant amount of positive charge at the nitrogen, and the negative charge distributes into the ring. Now, oxygen really is very much the same situation, but oxygen is also a lot more electronegative, and so you get a lot of negative charge still down at the oxygen. You know, Pyrrole, the charge separation is larger. There's actually, even though the nitrogen is more electronegative than carbon, the dipole for the molecule is pointing in this direction, as indicated by the blue that's down here and the red that's up here. For furan, the dipole is what you expect. It's pointing in this direction towards the more electronegative atom. Now that is principally because nitrogen is a better electron donating group than oxygen and isn't as electronegative as oxygen. This is a nice image showing why these different heterocycles are aromatic. For Pyrrole, there are 4 electrons from the pi bonds in the ring, and then there's 2 electrons from the lone pair, and these are all in p unhybridized p orbitals, which give us a total of 3 electron pairs. The molecule is flat, and an odd number of electron pairs makes it aromatic. Furan has the exact same structure. It has the 2 pi bonds here and here, and then the lone pair from the oxygen also is donated into the ring to make an odd number of electron pairs. Now, the other lone pair on furan is in a hybridized sp2 orbital, and this projects out away from the center of the ring and is in the plane of the molecule and can't participate in delocalization around the ring. The resonance contributors for Pyrrole are shown here, and you should have had some practice drawing these in the past, but again, these electrons move like that, and that produces this resonance structure, and then these electrons can move around like that, and again, and so forth. If you want to practice these, it's not a bad thing to do. Um, like this, and then one more to go back to the original structure. So that'll go back all the way over here. But what you'll notice in the resonance structures, most of the time there's negative charge on the carbons, right? And that is in each one of these structures, the negative charge moves around to be on one of the carbons, like that, okay? And so we have a negative charge in the ring and a positive charge on the nitrogen. Pyrrole is actually a very weak base because that lone pair that's on the nitrogen is needed for resonance. It also creates a situation where Pyrrole has a dipole which points in the opposite direction of pyrrolidine. Now, pyrrolidine is the saturated form of Pyrrole, and the nitrogen is the most electronegative atom in the molecule, and it draws the electron density towards the bottom and creates the expected dipole towards the nitrogen in the ring. And then Pyrrole has actually the opposite of what you'd expect based on electronegativity, and that's because in its resonance structures, the hybrid that's generated has negative charge pointed towards the ring and away from the nitrogen. As you may recall in Chapter 8 and a little bit in Chapter 18, we talked about delocalization energy, and that has to do with stability gained by a molecule or an ion by being able to delocalize its electrons in the ring. And the delocalization energy of aromatic compounds is larger than for simple conjugated compounds like butadiene, for example. So for benzene, what we find is the delocalization energy is the greatest. And then there's cyclopentadienyl anion, has the next highest delocalization energy. And then what we find is that the delocalization energy decreases as we go to more electronegative atoms in the ring. The reason for this comes from the fact that when you're looking at the resonance contributors from these different structures, one of the resonance contributors will look something like this for all of them. You have a negative charge here and a positive charge here. And because the oxygen is more electronegative than sulfur, it's not really good at holding a positive charge, and so the result is there's less delocalization resonance energy in these structures as the electronegativity of the heteroatom increases. When we look at Pyrrole and how it acts as a base, we see an interesting um, phenomenon. What we see is rather than the nitrogen protonating, Pyrrole tends to protonate in the number 2 position on the ring. Now, if the 2 position's occupied, then it might go to the 3 position. But again, looking at Pyrrole structure like this, this is 1, 2, 3, 4, and 5. The substitution or the addition of the electrophile, in this case the electrophile being hydrogen, almost happens exclusively at the number 2 position, unless that position is occupied by another group. The reason for this is not immediately clear until you draw all the resonance structures for what happens when you use hydrogen as the electrophile in either the 2 or the 3 position. This same kind of analysis could also be done with 6-membered rings and different other heteroatoms in the ring. And so it's important to sort of get an early grasp of this idea for understanding how these reactions, how the products play out in these reactions. So to start with, let's pretend that we protonate in the 2 position. And so we have Pyrrole, and it looks like this. Sorry, I left the hydrogen off that, but I was just showing the numbering on that one. And we take a hydrogen here. Now there's already a hydrogen here, so what's going to end up happening is this bond is going to break. Now, the way the book generally draws it is it generally draws it like this, and I actually don't have a real problem with it. It draws all these steps happening at the same time. So what you end up with is this. And this is a relatively stable structure. The reason we treat this as a relatively stable structure is because none of the octets are violated. So I may have a positive charge on the nitrogen, but I haven't violated the octet rule. So there are a couple of other resonance structures, but these aren't as stable. One involves the movement of the electrons to the nitrogen and forming the cation next to the nitrogen. And the positive charge is here. And then the third structure is this one. And it looks like that. Okay, so I have 3 resonance structures, one of which is relatively stable. The other two are not as stable because you violate at the carbocations. There's a carbocation here and a carbocation here. You're violating the octet rule. Now this is what happens when you add in the 2 position. Now to really to decide like what's going on, you really have to look at what happens when you protonate in the 3 position. So what we'll do is we'll do this. We're going to take Pyrrole and draw it again and pretend that we protonated in the 3 position. So what's going to happen is a hydrogen ion will be here. Again, this is the 3 position, so this bond's going to break. It could break on either side, really. And there's already a hydrogen here. And so this lone pair will fill in so that you don't violate the octet rule. And so then you get this structure. This is not a resonance structure. This is just a structure after the start of the reaction. So I have the hydrogens here. I have a nitrogen double bonded like this with the positive charge on the nitrogen. And then the only other resonance structure I can get is by breaking this bond and bringing the electrons back. So that's like this. So here's the important takeaway of this is that in order to determine where a reaction takes place, you have to actually look at the stability of the intermediate by looking at stable resonance structures and the number of contributing structures you have to your resonance hybrid. So for the case of Pyrrole, when you're adding at the 2 position, it adds primarily at the 2 position because you have at least one stable contributor, and the remaining contributors, there's 2 of them of about equal stability. For uh, for a substitution in the 3 position, what you end up getting is one contributor that's stable and then one other resonance structure that's moderately stable. And so because you don't have the same number of stable contributors to the structure, you end up having less stability. And so addition in the 2 position is what we typically see, or substitution in the 2 positions, typically what we see in the reactions of Pyrrole. Now, for 6-membered rings, so for example, pyridine, the position of addition or substitution is really different because in the initial addition portion of the reaction, when the electrophile is attacked by the ring, the resonance contributors dictate that the addition take place in the 3 position, and we'll see that later. But again, at first glance, there's not a good reason why we would expect 2 versus 3 versus 4, for example, in a 6-membered ring. And it turns out what you have to end up doing is looking at all the possible resonance contributors to sort of come to that conclusion of what is the most stable position for substitution. So another interesting property of Pyrrole in the presence of acid, or also a Lewis acid, so it could also be a metal ion, is that it will polymerize to form what's called polypyrrole. And polypyrrole is an interesting material because it's an insulator, but if you oxidize it, it can also be used as a conductor. The oxidation of pyrrole creates sort of a flexible conductive polymer. So, but in any case, as a consequence of protonating in the 2 position, what you end up with is you end up with an electrophilic 2 position on the other side, and that can act in an electrophilic addition reaction to attach to another pyrrole. And you'll notice what happens in the pyrrole that's next to it. What ends up happening is this is also an electrophile, so this will attach to another pyrrole, and then you'll end up getting a long chain polymer out of that. If you heat it, that is, you remove the hydrogen and you dehydrate it, um, you or do a do a dehydrogenation reaction to it. That's when you get the conductive polymer. Now, the pKa's are also affected. Of the pyrrole is also affected by resonance. It has a pKa of approximately 17. Now that's in contrast to something like cyclopentadiene. Cyclopentadiene's pKa is lower than that of Pyrrole, and that so I think it's around 15 if I remember right. It's lower than that because what ends up happening is when you remove this proton, it becomes aromatic. And then this is already aromatic, so removing the proton doesn't give it any additional stability. But the negative charge is still delocalized by resonance. Um, and if you look at in comparison to like pyrrolidine, in pyrrolidine the pKa is much higher, and that's because the pair of electrons that you put onto the ring don't get to don't delocalize by resonance. There are a number of nitrogen heterocycles, most of which you don't need to know by name. Pyridine, Pyrrole, pyrrolidine, those are ones that you should know. But from this chart, really the point of this chart is to show how the pKa's vary amongst the different nitrogen-containing heterocycles. So the ones that are saturated, for example, pyrrolidine, those are essentially um, the same as ammonia. The pKa's are high. The nitrogen is sp3 hybridized, and as a result, it tends to be relatively weakly acidic. On the other hand, Pyrrole has a nitrogen, but that lone pair, you have to remember, is delocalized into the ring. So effectively, this nitrogen is sp2 hybridized, and as a result, it tends to be a little bit more acidic. Um, the two nitrogen containing five-membered ring here, this is also more acidic, and the reason for an increased acidity is there's a lone pair that's on this nitrogen that's involved in delocalization, um, just like there is in Pyrrole, um, to make it aromatic. But the other thing is you have another nitrogen in the ring, and this is an electron withdrawing group. And if you remember inductive effects, the ability of when you have an atom that has the ability to withdraw electrons from the ring, that tends to make it more acidic. Um, Pyrimidine, this is a funny one. It is also very strongly acidic when protonated. Now, you'll notice that these are neutrals that are down here. Uh, Protonated versions, these are all the protonated versions of a bunch of different molecules, tend to be stronger acids because of that positive charge, and they want to dump that positive charge off. But if you look at pyridine and pyrimidine in comparison, you'll notice the pKa's are very different. One, this nitrogen is sp2 hybridized, so it has a lower pKa. And it's directly sp2 hybridized, it's not by resonance. So that's sp2 hybridized here. And so it has the low pKa. And the other thing is this has got a positive charge, right? So this is a neutral. So that's another reason for it being lower. Now, being sp2 hybridized here makes it more acidic, but you notice the pK of this protonated one's even more acidic, and that again is because of the electron withdrawing effects of that nitrogen. Either one can be protonated, but you can only protonate one, and then the pKa of the one that's protonated is relatively low. So that sort of goes over some of the acid-base properties and a little bit about the reactivity, and now what we're going to do is look at electrophilic aromatic substitution reactions. So you notice in these electrophilic aromatic substitution reactions of furan's another one you should know, and of pyrrole, this is methyl pyrrole or 2-methyl pyrrole, that the addition of the halogen occurs on the number 2 carbon. And this is for the same reason we talked about protonation occurring. We'll show the mechanism in a little bit, but in general, substitution in 5-membered heterocycles occurs at the 2 position. Now, the only time it doesn't occur at the 2 position is when the position is blocked. And if you remember in the mechanism, and that's what this methyl group, that's what this methyl group is doing here, is blocking that position. So if I do a substitution reaction on this, it'll go to the other side. If I have 2 methyl groups, so let's say I've created this, for example, then it'll go to the 3 position. Since the 2 positions are occupied by methyl groups, then the 3 position is the only position available. That's the position the substitution will take place at. For most of these reactions, you need some sort of Lewis acid catalyst. So if you remember for electrophilic aromatic substitution reactions of benzene, we used aluminum chloride and iron chloride, iron 3 chloride, as our Lewis acids to promote the reactions, or as catalysts for the reactions. And the same thing is true for these reactions, although to varying extents depending on which atom is in the ring, and we'll get to that shortly. Okay, so the mechanism goes like this, and it also explains why the methyl group acts as a blocking agent or blocking serves to block substitution at that position. The first step, which is the slow step because you're forming a carbocation, is the attack of the attack of the nucleophile on the electrophile. And then the fast step is the uh, deprotonation of the ring to get back to an aromatic ring. So the base, which of course we're in solvents which contain bases, the base then attacks the hydrogen and then forms the substituted aromatic ring. Now, if this had been a methyl group, then methyl groups don't usually come off very easily, and so the base can't take the methyl group like it takes the hydrogen, and you end up with this position being blocked. So if that's the case, if there's a methyl group here, then the substitution takes place on the other side. This is also showing why, um, um, sorry, why you can't, or why substitution takes place in the 2 position, right? That's up here. And again, it has to do with there being a relatively stable resonant contributor for both the 2 and the 3 position, but you get these additional 2 contributors for addition in the 2 position, and here you only have the 1. And so the additional resonance contributors lead to it being more stable so that it's the major product of the reaction. Oh yeah, sorry, there is a slide on this. I forgot about this. This is thiophene, and thiophene you have, or a dimethylthiophene, I guess to be technical. Thiophene is without the methyl groups. If those positions are blocked and you do the halogenation, then the halogenation occurs in the 3 position. Now, in terms of reactivity, it turns out that all the substituted or all the heterocycles are more reactive in benzene. And the reason for that is because the heterocycle acts like an internal electron donating group and increases this because of its ability to donate electrons, and it's in the ring, right? It is able to accelerate the rate of the reaction by stabilizing the carbocation that forms. Nitrogen is much more the Pyrrole is much more reactive than furan because nitrogen is less um, electronegative than oxygen. And if you remember, a positive charge in the intermediate builds on this heteroatom, and as a result, lower electronegativity allows it to be more stable. Thiophene, on the other hand, is less reactive than oxygen, and that's because sulfur is using 3p orbitals, and the carbon that's adjacent to it has 2p orbitals. So that's a horrible 3, sorry. The ability for the sulfur to donate electrons to the carbon is not as efficient as the oxygen, which is also using 2p electrons, right? As the oxygen, because the orbital sizes are matched better. Now, here's some examples of reactions that take place for benzene, thiophene, furan, and pyrrole, going in this order, right? These are acylation reactions. And remember, acyl halides are very reactive. This is the Lewis acid catalyst. The mechanism's the same as we learned in the previous chapters. But the Lewis acid catalyst serves to remove the chlorine and essentially make this more electrophilic. It turns out that if you change the Lewis acid catalyst, now this is a strong Lewis acid. And this is a weaker Lewis acid. Lewis. Wow, I didn't spell that very good. The weaker Lewis acid gets to be used because the oxygen is a better activator in the ring than the sulfur. tin is slightly more reactive. And then with benzene, you have to have a really strong Lewis acid. And it turns out for Pyrrole, you can use, this would be an anhydride. Remember, anhydrides are less reactive than acyl halides. You can use an anhydride because the nitrogen is so activating, you don't need a catalyst. There's no catalyst needed for that reaction. Let's see. Okay, so what we'll do next is we're going to go into the reactions of pyridine, but I'm actually going to break the lecture at this point. I think this is a good stopping point. Pyridine and Pyrrole, many of the concepts are the same, but like I talked about before, um, what we'll be getting is addition in the 3 position rather than the 2 or the 4 position. Again, it has to do with the resonance contributors, and so essentially the concepts are the same for electrophilic aromatic substitution reactions. The only other real difference is that this pair of electrons in pyridine is nucleophilic, whereas the one in Pyrrole, because it's involved in resonance, is not nucleophilic. So we'll pick up from here, and that'll be the next installment of this chapter.